Alright, today is section 8.4 we're going to cover. The book entitles it Quadratic Functions and Their Graphs. I'm going to entitle it simply Graphing Parabolas. Alright, let me give you an example of a quadratic function. Well, a quadratic function is a function that is defined by a quadratic polynomial or a polynomial of degree 2. I suppose the simplest quadratic function you could have is f of x equals x squared. That is a function defined by a degree 2 polynomial expression. If I ask to graph this degree 2 polynomial function, this quadratic function, well, we can do this pretty easily. Making a table of values, I'll have an x column and a f of x column. If x is minus 3, of course, f of x is 9. If x is minus 2, f of x is 4. If x is minus 1, f of x is positive 1. If x is 0, f of x, of course, is going to be 0. And on down the line, if x is 1, f of x is 1. If x is 2, f of x is 4, and we'll see these values repeating. If x is 3, f of x is 9, and down the line. Alright, the idea here is to establish a pattern. Once we recognize a pattern, we'll stop plotting points and finish and label the graph. I'll do the best I can on the tablet here. I can't really use a ruler on the tablet, at least not easily, so I'll do my best to do it freehand. Let me plot these points in the xy plane. If x is minus 3, y is positive 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll put it up here. If x is minus 2, y is 4. 1, 2, 3, 4. I'll put it here. If x is minus 1, y is 1. If x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 4. And I think we get the idea here. Alright, if I plot these points in the xy plane, it looks like a familiar object. You get what they call a parabola. And let me see. I did a terrible job of connecting the dots. Let me try it again. Alright, minus 3, 9, minus 2, 4, minus 1, 1, 0, 1, 4, 9. Alright, let's see if I can do a better job connecting these dots. We've got a parabola. Here we go, a little bit better. Alright, and both ends of this parabola go off to forever in both directions. I'll call this a graph of f of x equals x squared, and that's everybody's first parabola, graph of parabola. Okay? Alright, long and short of it is a graph of a degree 2 polynomial will always give you a parabola. Let me write that down. Graphs of degree 2 polynomial functions. Well, remember, degree 2 polynomial functions are what the book calls quadratic functions. And these things are parabolas in the xy plane. Alright, now there's all kinds of parabolas. There's short, fat parabolas. There's tall, skinny parabolas that may be located all over the xy plane depending on the value of the coefficients. This is what they call a concave up parabola because it bends up going left to right. We're always bending up going left to right. This, of course, is called a concave down parabola. And as you see, going from point to point, left to right, we're always bending down in this parabola. Alright, general form of a a quadratic function, I guess you could call it a parabolic function, looks like this. F of x equals ax squared plus bx plus c. And of course we use the symbols y and f of x interchangeably. Right? We usually reserve the letters f, g, and h for function notation. If your lead coefficient is positive, your parabola is concave up. Right? If your lead coefficient is negative, your parabola will bend down, will be concave down. All right, we already saw an example. We graphed f of x equals x squared, or 1x squared, and a was 1 in that example we just did. And of course, we had a parabola that was concave up. Let's try a concave down parabola. And again, the graph of any degree 2 polynomial equation will always be a parabola. Where it's located and how wide or narrow it is to be determined. Depends on the coefficients a, b, c. Alright, g of x is minus 2x squared. I'm going to plug in some values of x here and see if I can get a table of values and plot these points. If x is minus 2, g of x is then negative 8. If x is minus 1, g of x is going to be minus 2. If x is 0, g of x is 0. If x is 1, g of x is minus 2. And if x is 2, g of x is minus 8. Alright, so I'm going to do my best to sketch a graph here in the xy plane. Alright, let me try those axes again. I want to be sure to leave enough room here for this particular parabola. I think we're going to be traveling more in the negative realm than in the positive realm. So let me try it like this. Alright, so here's my xy plane. If x is minus 2, y, or g of x, is going to be minus 8. 1, 2, 3, 4, 5, 6, 7, 8. I'll put it right here. If x is minus 1, y is minus 2, or g of x is minus 2. If x is 0, g of x is 0. Remember, we use the terms y and g of x interchangeably here in this example. If x is 1, y is minus 2. Let me fix this one. This one is a lot of place here. Again, doing the best I can. Freehand. And if x is 2, y is minus 8. I think we get the idea here. This is a concave down parabola, bending down, going left to right. Alright. And we confirm that with the lead coefficient being negative. So if a is minus 2, a here is minus 2 in this problem, that implies your parabola will bend down. We call that concave down. Alright, so two simple parabolas so far. One concave up, one concave down. Now, look at this. We had 7 points to graph this parabola. We had some 1, 2, 3, 4, 5, 7 points to graph this parabola. We could have even used more. I claim, using this system I'm about to give you, you can graph a parabola with 3 points. Let me write this down. Claim. We can graph a parabola, a degree 2 polynomial equation, and get a nice picture, see all the action. We'll see the turning point and axis of symmetry and etc. with as few as 3 points. You can graph a parabola with 3 points if you pick those points correctly, and I'm going to give you a little system to do that. Before we do that, we need some definitions. I claim all parabolas, fat or skinny, up or down, have an axis of symmetry. And I'm sure you've heard that phrase before. It's the vertical line about which the parabola has vertical symmetry. Okay? Each parabola also has a vertex, and the vertex is the intersection of the parabola itself and the axis of symmetry. And of course, the parabola is the graph of the quadratic function of interest. Alright, so on the way to graph our parabola, we're going to be finding the axis of symmetry. I'll show you how to do that. We're going to be finding the vertex, and then we're going to be finding two what we call symmetric points that'll give us an idea of how wide or narrow the parabola is. Alright, new screen. Alright. To graph parabolas. Step 1. Find the axis of symmetry. Now, the axis of symmetry is the vertical line x equals minus b over 2a, where of course a, b, c are the coefficients of the quadratic equation of interest when the terms are arranged in standard form. Okay? Alright, axis of symmetry, x equals minus b over 2a, a simple formula that will give you the axis of symmetry. Step 2. Find the vertex. Well, the vertex is by definition on the axis of symmetry. Remember, if you've got a parabola and you've got an axis of symmetry, the intersection of the axis of symmetry and the parabola is the vertex. Alright? Well, the vertex can be found with this very simple formula. Since the vertex is on the axis of symmetry, you can find the coordinates of the vertex by letting x equal minus b over 2a and solving for the unknown y coordinate using your original quadratic function. I'll show you how to do that in a minute. And step 3, once we identify the axis of symmetry, once we identify the vertex, then we have to find how fat or skinny this parabola is. And to that end, I'll say find two what we call symmetric points. Find two symmetric points. I'll put that in quotes because as often there's different ways to do that depending on the situation you're encountered. Typically, the first few times out, we can find the X Intercepts. I'll put a question mark there, a couple of them, because it's not always possible to find X Intercepts, and it may not always be very easy to find the X Intercepts. The first couple problems we do, that'll be easy enough, but later on in the later examples, we'll have to do something else, and we'll talk about that when we get there. Okay? So, I'm going to give you an example of how to invoke this three-step system to find a graph of a parabola. Here we go. Graph h of x equals x squared minus 2x minus 3. Alright, this is a quadratic function. Basically, it's a function determined by a quadratic polynomial, a degree 2 polynomial. Well, a graph of a quadratic function is always a parabola. Alright, what I'm going to do is let h of x equal y. Again, we can use the terms h of x and y interchangeably. First step is to find the axis of symmetry. I'll abbreviate that as AOS. Alright, one thing I want to note here is the graph is going to be concave up I know that because it's in standard form and my lead coefficient is a positive 1. Right? A is greater than 0 means your parabola is going to be concave up. So is it going to be concave up fat or concave up skinny? That's to be determined by our symmetric points. In any case, we're going to find the axis of symmetry first. The axis of symmetry can be found according to this very simple formula: x equals minus b over 2a, assuming your quadratic polynomial is already in standard form. Well, b is negative 2 here, so minus b over 2 times a is positive 1. Well, that'll of course give me the expression x equals 2 over 2, or x equals positive 1. All right, the axis of symmetry, it's not 1, it's the equation x equals 1 is the vertical line. Remember, if x equals constant in the xy plane, you've got a vertical line. Is the vertical line x equals positive 1. Alright, so step 1 is done. I found the axis of symmetry. Alright, let me go ahead and sketch it. Alright, x equals 1. I'll put that in a different color. It's not the parabola. It's a vertical line that defines symmetry of the parabola. Okay? So x equals 1. I'll sketch my axis of symmetry and label it. X equals positive 1. Okay? Step 2. Find the vertex. Well, the vertex is on the axis of symmetry, is it not? And if the axis of symmetry is the line x equals 1, that means your vertex will have an x-coordinate of 1. So what I have to do is find y when x is 1, and I can do that by plugging 1 into my original equation quite easily, right? What is y when x is 1? Just plug in x equals 1 and find out. So I do y equals 1 squared minus 2 times 1 minus 3. 1 squared is 1. 1 minus 1 is 0. And 0 minus 3 is, let's see, hang on a minute. 1 squared is 1. 1 minus 2 times 1 is minus 2. And 1 minus 2 is negative 1. And negative 1 minus 3 is minus 4. Alright, so please convince yourselves that when x is 1, y is minus 4. So my vertex is going to have the coordinates 1, comma, minus 4. Alright, so let me go ahead and graph that vertex. When x is 1, y is minus 4. And I'll label that point as my vertex. 1, comma, minus 4. Alright, next thing I'm going to do is find two symmetric points. Now, I don't want to lose the graph in the screen, so I'm going to erase this here. You can rewind to get back there if you need to. Let me put step 3 here. Find two symmetric points. Again, we need some sense of how wide or narrow this parabola is. Okay? Well, if the X intercepts are easy to find, it may be a good idea to find the X intercepts. Okay? And I think we can find the X intercepts of this parabola pretty quickly if I consider the original equation, y equals x squared minus 2x minus 3. Well, how do you find the X intercepts? You set y equal to 0 and solve for x. Well, in this particular problem, we've got a polynomial expression on the right that factors pretty easily. Alright, so I can find this solution by factoring. I'll get, let's see, I'm going to get 3 1. Let's see, I'll do x minus 3 times x plus 1. I think that factors it correctly. So I'll get two x-intercepts, two solutions for this equation, x equals minus 1 or x equals positive 3. Alright, so let me graph those x-intercepts. If x equals minus 1, well, this is 0 here. Minus 1 puts me here somewhere. Let me label that point. When x is minus 1, y is 0. And how about the other one? Well, if this is 1, 2, 3 puts me here. So when x is 3, y is 0. Alright, so those two symmetric points, and they had better be equally distant from the axis of symmetry, else you've made a mistake. Those two x-intercepts do give me a good sense of how wide or narrow this parabola is. So I've got the axis of symmetry, the vertex, two symmetric points. Just connect the dots. We know it's going to be a parabolic shape. We know it's going to be a concave up parabola. There, finally got all the dots. Nice. So there is the graph of my parabola, and of course I need to label the parabola with the equation that generates it. H of x or y equals x squared minus 2x minus 3. Alright, so 3 points graphs you a nice parabola if you pick your points correctly. Okay? Alright, let's try another one. Oh. Hang on, what did I do here? Alright, there we go. Graph the following degree 2 quadratic function. Y equals minus x squared plus 4x plus 5. Alright, so this one's given to us not in function notation, but that's fine. Y is an implied function of x here. I notice this is going to be a concave down parabola. Alright, if a is less than 0, if you're in standard form and your lead coefficient is negative, your parabola is going to be concave down. Okay? Step 1. Find the axis of symmetry. I'll abbreviate that as AOS. And the axis of symmetry is the vertical line x equals minus b over 2a. Well, in this particular problem, it's x equals minus 4 over 2 times negative 1. Right? And minus 4 over 2 times negative 1, well, negative over negative is positive, it's going to be x equals 2. So the axis of symmetry is the vertical line x equals positive 2. Alright, before I sketch anything, let me find the vertex. That's step 2. The vertex is on the axis of symmetry, and the axis of symmetry has x coordinates of 2. So that means the x coordinate of the vertex must be 2, and I need to solve for y to find the y coordinate of the vertex. Alright, so when x equals 2, I'll plug in y equals minus 2 squared plus 4 times 2 plus 5. And solve for y. Alright, be careful about the sign here. Square first, then negate. So this minus 2 squared is minus 4. Plus 4 times 2 is 8. Plus 5 is going to be, well, minus 4 plus 8 is 4. And 4 plus 5 is 9. So y equals 9. Alright, so we've got a concave down parabola with a vertex of 2, 9. Alright, let me start sketching some stuff here. Oop. I seem to do better over on the right hand side. Try that over here. There's my y-axis. Here's my x-axis. The axis of symmetry is the vertical line x equals 2. Alright, so let me sketch it here, and I'll do the best I can to do it, and I'll do it in a different color to differentiate it from the parabola itself. Alright, and I'll label the axis of symmetry x equals 2. The vertex of the parabola is the point 2, 9. So when x is 2, y is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Puts me here. And I'll label it 2, 9. Vertex. Now remember, this is going to be concave down. Alright, how wide or narrow is this parabola going to be? So I need 2 symmetric points. Now if the x-intercepts are there, if they're easy to find, and sometimes they're not, I'm going to go ahead and find the x-intercepts. So let me look at my original equation. Y equals minus x squared plus 4x plus 5. To find your x-intercepts, you set y equal to 0 and solve the resulting equation for x. And I think I see this factoring and solving pretty easily. Let me go ahead and get it in standard form with positive lead coefficient. And yes, indeed, it does factor. So the x-intercepts are going to be easy to find. Not always going to be true. Alright, so 5 and 1, I think if I get a minus 5 and a plus 1, that'll do it. So I've got x-intercepts at x equals minus 1 or x equals positive 5. Alright, so let me graph these 2 points. X equals minus 1 puts me here, and 2, 3, 4, 5 puts me here. And again, these points had better be equally distant from the axis of symmetry, and they are. So let me go ahead and label them. This point, this x-intercepts has coordinates minus 1, 0. Okay, cleaning things up a little bit. And this point here, this x-intercept has a coordinate 5, 0. Alright, so I have everything I need. I've got an axis of symmetry, I have a vertex, I have 2 symmetric points. I know it's going to be a concave down parabola. Alright, so I'll connect the dots as indicated, and that gives me a good picture of the parabola with all the action shown with as few as 3 points. Of course, I should label the parabola with the equation that generated it, y equals minus x squared plus 4x plus 5. Okay? Alright, so label your axes, label the vertex, label the symmetric points, and of course label the parabola equation that generated the parabola picture. Alright. Let's see. Let's try another one here. New screen. Let's see. Graph the following quadratic function: x squared plus 2x plus 1, or y equals x squared plus 2x plus 1. Alright, we'll take it step by step. Step 1, find the axis of symmetry. Well, it's already in standard form. So I claim the axis of symmetry is the vertical line x equals minus b over 2a, and that of course is the vertical line x equals minus 1. Alright, I'll graph that in a minute. Step 2. What's my vertex? Well, the vertex is on the axis of symmetry. So the vertex must have an x-coordinate of minus 1. So if I plug in minus 1 to the original parabolic equation, I should be able to find the coordinates of the vertex. Right? So y equals minus 1 squared plus 2 times minus 1 plus 1. Well, y equals minus 1 squared is 1. 1 plus minus 2 is negative 1, and negative 1 plus 1 is 0. Alright, so my vertex then is the point minus 1 comma 0. Alright, notice the original parabolic equation tells me it's going to be concave up because my lead coefficient is a positive 1. And when I see a vertex with a y-coordinate of 0, well, that tells me something. That tells me there's only going to be one x-intercept here. So, as I was foreshadowing before, you don't always have two x-intercepts, and sometimes they're not even easy to find, even if there are two. So, let me highlight step 3. We have to find two symmetric points. And here the x-intercepts are not going to satisfy because there's only one of them, as we'll see in a minute. Let me start graphing this stuff. The axis of symmetry is x equals minus 1. The vertex is minus 1, 0. Right, let me start putting some of this stuff down. The axis of symmetry is the line x equals minus 1. The vertex is the point minus 1, 0. And we know it's going to be a concave up parabola. Let me show you what I'm talking about here. Alright, we're in the xy plane. And let's see, the axis of symmetry is the vertical line x equals minus 1. Alright, so let me do the best I can to draw a vertical line with all these x coordinates being minus 1. Alright, so I'm going to label my axis of symmetry. Alright, the vertex is the point minus 1, 0. Alright? And if your vertex has an x-coordinate of 0, I think you'll see, well, the parabola, well, either it's going to be fat through minus 1, 0 or skinny through minus 1, 0. The idea here, if your vertex has a 0 y-coordinate, there's only going to be one x-intercept. So to find two symmetric points, we're going to have to do something else than to find the x-intercepts, because there's only one. Find two symmetric points. Alright, there's a nice little trick we can do here. And let me highlight this. X-intercepts? No, it's not going to work. Not for this problem. It worked for the last two, but not for this one. Alright, well, what are we going to do? If we look at the original equation, y equals x squared plus 2x plus 1, what I can do is spot the y-intercept. Right? The y-intercept, well, if x is 0, we can easily see when x is 0, y is 1. So when x is 0, y is positive 1. Well, what I can do, let me see if I can get a straighter y-axis here. Give me a second. A little bit better. Alright. So the y-intercept is 0, 1. So when x is 0, y is 1. Now notice that's not the x-intercept. Let me label it. This is the y-intercept. What I can do is say, because of symmetry, there's a spot equally distant, or a point equally distant on the parabola on the other side of the axis of symmetry. So I think you can see, if I've got a parabola point at 0, 1, I'll just count over. Well, there's 1 unit of distance from the y-intercept to the axis of symmetry. There must be another 1 unit of distance to establish a second symmetric point. So there's a nice little trick. I claim it's, or I call it, you find the y-intercept and count over to establish a second symmetric point. Alright, if this y-intercept has coordinates 0, 1, of course this symmetric point has coordinates -2, 1. Right? And I now have the axis of symmetry, the vertex, 2 symmetric points. I can go ahead and connect the dots to establish a parabola picture. And of course you must label the parabola with the equation that generates y equals x squared plus 2x plus 1. Alright. Let's try one more. Yeah, this will be the last one today. Graph. And it'll be another degree 2 polynomial equation. In other words, the graph is going to be a parabola. Of course, this parabola is going to be concave down. I know that because your polynomial is in standard form and your lead coefficient is negative. Step 1. Find the axis of symmetry. Well, that's going to be, according to the equation, x equals minus b over 2 times a. Right? So it's going to be positive 4 divided by negative 2. Your axis of symmetry is the vertical line x equals minus 2. The vertex. Well, the vertex occurs on the axis of symmetry. That means when x is minus 2, I can solve for y in my original equation statement. So y equals minus 2 squared minus 4 times minus 2 minus 4. Y equals minus 2 squared is 4, so I'll have minus 4 plus 8 minus 4, or I get the y coordinate, y equals 8. Okay? Oh, sorry, made a mistake. Check it. Minus 4 plus 8 minus 4. Of course, that reduces to 0. So I get y equals 0 on my vertex. Alright, so the vertex is the point minus 2, 0. Alright, let me plot those two quantities and then talk about symmetric points. Alright, so there's my y-axis. Here's my x-axis. The axis of symmetry from above is x equals minus 2. The vertex is, of course, the point minus 2, 0. Alright, so x equals minus 2. Vertical line with the x coordinate of minus 2. And it doesn't look too bad. Getting better at it, I think. And let me label the axis of symmetry. The vertex is minus 2, 0. Well, there's the vertex. And let me label it Alright, now we know this is a concave down parabola. We already secured that up above. Alright, so I have to find two symmetric points. Now again, here I'm only going to have one X-intercept. The vertex is on the x-axis, hence there will only be one X-intercept. Right. So X-intercepts aren't going to work here. So what I'm going to do, like in the last example, I'll find the Y-intercept. That's usually very easy to find. And I'll say count over to establish a second symmetric point. Let me write down the original equation. Y equals minus x squared minus 4x minus 4. Alright, to find the y-intercept, you set x equal to 0. So if x equals 0, that means from this equation I can discern y equals negative 4. So my y-intercept is going to be the point 0, comma, negative 4. So when x is 0, y is negative 4. I'll label it. That's my y-intercept. And now I can establish a second symmetric point by counting over. I see there are 2 units of distance between the y-intercept and the axis of symmetry. Hence there must be 2 units of distance on the other side of the axis of symmetry to establish another symmetric point. Alright, so if this point has the coordinates 0, minus 4, there's a symmetric point equally distant on the other side, and of course that's going to have the x-coordinate minus 4. So this point has the coordinates minus 4, minus 4. The y level is the same. Alright, so I'm just about there. I established 2 symmetric points. I already have the axis of symmetry and the vertex. With these 3 points, I get a nice picture, see all the action, see the turning point, the axis of symmetry, 2 symmetric points, and a nice picture of the parabola with 3 points. Of course, we need to label. The parabola with the equation that generates it, and we're done with this example. Alright, that's the last one for today. Kind of a long class, but yeah, it's kind of a long topic, I guess, a little bit of a harder topic. Alright, so we'll call it a day at 43 minutes for section 8.4, quadratic functions and their graphs.